Hi. In the previous video, we've seen how we could compute an Hermite curve, and the Hermite curve is using 2 point and 2 tangents to draw a curve in between. And we started to paste a few of those back to back so we could have a spline automatically drawn between all the points. What we want to do now is actually having the fact that we can have a bunch of points and have a function that goes through those points. So really an interpolation spline without the need for us to compute that tangent of each point, but to just let the data itself decide what the tangent would be. And that's what the cardinal spline is. The cardinal spline basically takes a bunch of points and compute the tangent for us at each point, so we could use a Hermite curve in between. How it does it, it's basically taking for specific points, it takes the point after the point before, draw that line between the two, and that's the tangent that we'll be using for that point. And then we have a S factor in front of that tangent, so we could decide to scale it up and down to give it more importance or less importance when we draw the curve itself. So I have a function here that is a cardinal to Hermite with the S factor. Basically takes a bunch of points and returns a list of point, tangent, derivative every time, so we could pass that to the Hermite functions we had before. And if I draw this, basically that's what it gave you. You could see that, of course, the first point and the last point, you don't have any curve coming in or out of it. That's just because we don't have enough points before or after to compute what the tangent will be for this guy. But you have that S factor that can decide how big is the tangent. So if I bring it that S to 0, I'm basically scaling down completely my tangents. So I have linear interpolation between all of my points. And I can go up and go as crazy and having really weird curves by increasing the tangent size for my function. Now, it works. The only issue we have with this kind of system is that the S factor is not really intuitive to use. It doesn't represent much except for mathematical purpose. Usually when we start to work with splines, it comes from the drawing and the physical world. So we tend to want to use something that is more meaningful for the user. So what we have is a tension parameter instead. The tension parameters make more sense in the physical world, because imagine you were trying to draw a spline using rope and paper. What you will have to think about is the tension you put inside of your string will actually decide what type of curve you're drawing. If you put a really hard tensions, you basically have a line, and if you let it completely loose, you will have a nice curve. So we tend to use tension because it's clearer to use as a concept. And so what we have is the tension parameters that can go between 0 and 1. 0 means 0 tension, I have a nice curve. 1 being I'm pulling on my string maximum, and I have a line, basically, a straight line. So how do you compute that tension? Basically, it gives you your S factor from the previous algorithm, but what we have is 1 minus my tension divided by 2. And so with a t that goes between 0 and 1, a tension that goes between 0 and 1, what you have is that at 0, you have an S that is equal to 0.5, and at 1, you have an S that is 0. And a S that is 0.5 actually is a Catmull-Rom spline. So if you are interested in animations, you probably have heard of the Catmull-Rom spline. And basically, it's a specific case, and it's a cardinal spline with a S value of 0.5. That's it. So what I have now is my function that is a cardinal to Hermite. Again, works the same way. So I gave a list of points and returns a list of points and derivative. Except that I pass the tension now directly in, and I compute my S using my tension, and then everything else stays the same. So if I execute this, and I execute my functions, now I have a function that is drawn, and you can see that with a tension of 0 I have smooth functions, and with a tension of 1 I have linear functions. you might have noticed that now I actually have drawn from the 0 up to the last point. And the way to do this, it's actually by repeating the first points and repeating the last points inside of my list. So you always have something to compute that that tangent. Now, what we've done so far is still using the Hermite curve functions we had before, and having a function that goes from cardinal to Hermite and then use the Hermite to draw the curve itself. What we can do is to try to directly find a mathematical function that allows us to directly render a cardinal spline without the need to go through the Hermite function. And to do this, what we will do is basically start from the Hermite function. So I've started with the Hermite function as what it was, with the matrix form, and ask SymPy to compute it, and I get that formula, the one we have already seen, with the P1 multiplied by 2t cubed and so on, and then you get the delta, the derivative 0.1, derivative 0.2, and all that kind of stuff. What I've done is, instead of using 0.0 and 0.1, like we had before, what I did is that I used 0.1 and 0.2. So I have a curve that is drawn between 0.1 and 0.2. But it's just the same formula. I've just changed the letter, basically. Now, what I can do is I know how the cardinal spline will actually compute my derivative for 0.1 and my derivative for 0.2. So I can use that function here, and I can replace the derivative of 0.1 by the actual formula, which is the S P2 minus P0, and the same for the delta, the derivative 0.2. It's the S.3 minus 0.1. And if I, again, ask it to solve for this and write it as a P0, P1, P2, P3 function, you could have now really a P0, P1, P2, and P3 function directly with all the factors here. And then we don't have the derivative anymore inside of our matrix, but what we have is a bunch of S that represents our curve. So I can now write this again as a matrix and see, again, it's the same structures as the matrix for the Bezier curve, the matrix for the Hermite curve. Now it's a matrix for the cardinal spline using directly the S inside of that matrix here. And I can have my cardinal functions now that directly draw a curve and doesn't go through the step of giving me a list of Hermite spline and that kind of stuff. And if I execute this, now what I could do is, of course, render directly that same cardinal spline as the one I had before, except now that I directly compute the cardinal spline just using the points and not doing the intermediate step. Now, there is one particularity to the cardinal spline, and what it is that it says that at best, a cardinal spline has a C1 continuity, and that might be a confusing term, but basically what it means, a C0 continuity means your function, the continuity inside of a function. So a continuous function is a function where you could always keep drawing with one step. You don't have to lift your pen, basically. So you don't have discontinuity in your function. So at the C0, you have, well, for the function itself, it's continuous. You could see that with a hard tension, of course, even the C1 is my first derivative. I can see that my first derivative now is completely discontinuous. And it said that at best you could have a C1 continuity. So if I go with a really smooth function cardinal spline, you could see that I have my C1 continuity here. Actually, my derivative is continuous function also. But then if I try to get a C2 continuity, which is the second derivative, you could see that I don't have continuity inside of my C2, well, my second derivative. What that means is usually it's more important if we talk about animation in the sense of, I don't know, physics and that kind of stuff. If my spline, my cardinal spline here is, for instance, a curve that represents the position of my object in time, and I want my object to follow that curve, what it means is that C0 is the position of my object. My first derivative is the speed of my object at every time, and my second derivative is the acceleration of my object. And you can see that I have discontinuity inside of my acceleration every time. Might be visible, might not be an issue depending on what you want to do. Every spline does compute different stuff. So the cardinal spline has at best a C1 continuity, and then we will see in the next video another type of spline that can actually give us a C2 continuity, and see you next time.